Hi everybody, welcome back to the Feynman technique. All right, today I've got a really difficult integral that we're going to solve using a combination of Feynman integration and complex numbers. A lot of the steps are going to be very abbreviated, otherwise this video would be extremely long if I showed every single step along the way. I'm going to leave out a lot of the steps that you guys would have no problem doing on your own. So let's just get started. Um, the first thing we're going to do is recall this, and I have derived this expression on this channel before. Um, you can get this by well, we know that the integral of 1 over z squared plus 1 is arctangent z, and you can split up 1 over z squared plus 1 into 1 over z plus 1 times z plus I times z minus I. Use partial fractions and then integrate individually, and you will see that that is actually true. So we're going to be using that to solve this integral. So using that formula, we can see that our original integral is just going to be I over 2 times the integral from 0 to pi over 2 of the natural log of, well, we're plugging in sine squared x for our z. So this is true right here. So the next thing we're going to do is we're going to create a function of t that's equal to the integral from 0 to pi over 2 of natural log of 1 plus t times sine squared x dx. And you can probably see why I did that. That is because our integral is now I over 2 times the quantity of f evaluated at negative I minus f evaluated at I. Go ahead and pause the video and check that out. But it is true if you plug in negative I and then subtract f of I, you will get, and then multiply it by I over 2, you will get um, our integral. And we'll also note that if we evaluate f at 0, we get 0. All right, so next step, we are going to differentiate f of t with respect to t using the Leibniz rule for differentiation under the integral sign. And here's where I skip a little bit of the steps. We can take the derivative directly of our f of t by just taking the partial with respect to t of the integrand. And if you do that, you'll see that the integrand becomes this. And then we can actually evaluate that integral. It's not that bad, um, but I'm not going to show the steps for that. But that's what it turns out to be. This integral right here actually evaluates to this, and you can use standard integration techniques to see that. So next, we'll just note that our original f of t is equal to the antiderivative of f prime of t, which is this right here. So our f of t is pi over 2 times this integral right here. And again, I'm not going to show the steps, but you can anti-differentiate that easily enough to get this expression right here. And now we will use the fact that we know that f of 0 is equal to 0 to see that c has to be negative pi natural log 2, and that will give us our final expression for f of t. So f of t is pi natural log of the square root of t plus 1 minus pi natural log 2. And now don't forget our original integral is just this is f evaluated at negative I minus f evaluated at I times I pi over 2. We have that right here. So let's show that. So I is now, again, I over 2 times our f evaluated at negative I, that's right here, minus our f evaluated at I. And you'll see that this minus pi natural log 2 minus a minus pi natural log 2, that cancels. So this is our expression for I right now. Of course, we don't want to, we could leave it like that. I mean, that is absolutely true. But we don't want to leave I in our expression for big I. All right, so let's rewrite it a little bit. You can see what I did is I rewrote this square root of 1 minus I as the fourth root of 2 times e to the negative I pi over 8. Because 1 minus I is just square root of 2 times e to the negative I pi over 4. And then taking the square root of that, you see we just get 2 to the 1/4 e to the negative I pi over 8 plus 1. And likewise for this expression, we have almost the same thing, except it's not e to the negative I pi over 8, it's just e to the I pi over 8. And then I broke up e to the I pi over 8 and e to the negative I pi over 8 into its cosine and sine parts. And we can do that and get this. All right, so now our expression for I is expressed like this. So let's see what I did in the next step. Ah, that's right. Okay. So the natural log of a complex number a plus bi is equal to the natural log of our component a squared plus our component b squared divided by 2 plus I times the arctangent of our b component divided by our a component. So using that formula on our expression for I, and now, well, actually, first, I just want to say that this natural log right here, this right here, can be converted using this formula into this minus this. Go ahead and verify that for yourself if you'd like. All we're doing is we're using this formula right here on this right here, where our A is this and our B is minus this. Okay. And then, of course, we're going to do the same thing for the natural log of this expression, where our A is this and our B is this part right here. So now we have this is equal to this and this is equal to this, plugging them back into our expression for I, and we get this. So our I is now just equal to this natural log minus this natural log. You can see, you can go ahead and pause the video and kind of see what I did there. We know that this is equal to this, and this part right here is just right there. And there will be some cancellations. In fact, the cancellation is going to happen with these parts right here. So what we end up with is this. All right. And this is actually the answer right here. I pi over 2 times the natural log of this minus the natural log of this is just this. Again, go ahead and pause the video and plug in the numbers yourself, but you'll see that it turns out to be this. And then we'll just, I don't want to leave this cosine pi over 8. Cosine pi over 8 is actually the square root of 2 plus the square root of 2 all divided by 2. That can be shown using the half angle formula for sine and cosine. And we also have sine pi over 8 is equal to this right here. So plugging those in, we have that I is equal to pi times the arctangent of this over this. And then doing some simplification here, we get this. All right, and that is it. That is actually the answer. There's a lot of 2's there, a lot of 2's. So finally, there's our integral solved. So the integral from 0 to pi over 2 of arctangent of sine squared x dx is pi times the arctangent of the square root of 2 times square root of 2 minus 2 divided by the square root of 2 times square root of 2 plus 2 plus 2. Okay, guys, I hope you enjoyed that, and we will see you next time.